Blake Richards is at McGill University in the Neurological Institute, as well as the computer science department. His specialty is the phenomenon of prediction and, can I call it error correction?
Sure, that works.
OK. Et puis, je vais dire ça en français aussi. Blake Richards est chercheur dans le département, à l'Institut neurologique ainsi que le département d'informatique à McGill. Et puis, son domaine de spécialisation, c'est la prédiction et la correction d'erreurs. Avec ça, I hand it over to Blake. Oh, last thing, Blake. Do you want to be interrupted, or do you want to save all questions till the end?
I'm happy to be interrupted.
Okay. So, and I don't know if you can handle French questions. If there are French questions, I'll translate them.
I should be able to handle them, but si je comprends pas, je vais te demander.
Je serai là. Okay, go ahead.
Very good. So hello, everyone. As Stephen said, my name is Blake Richards. And so I'm going to give you a very high-level kind of overview talk today, because I was told to make it quite general. I'm happy to be interrupted, as said. Let's just keep this fun and informal. So what I'm going to talk about today is a kind of broad claim that I would make, which is that understanding, or what we call understanding, is ultimately an emergent property of learning to predict the world. So that's my broad claim. And another way of phrasing this is that, you know, understanding is something that happens in systems that have been optimized via evolution or learning to engage in prediction. And the way I'm going to build an argument for this broad strokes claim is to show you how, at the computational and behavioral level, we can see that AI systems that are optimized for prediction exhibit a lot of what we would be inclined to call understanding, and what I will just straight out call understanding. We can discuss the sort of philosophical, hairier stuff towards the end of the talk. I do return to this, do not worry. I know this is a cognitive science audience, and so one can never engage in pat statements like this without having the specific usage of the words questioned. But nonetheless, I think what we see in these AI systems is what we would call understanding. And furthermore, what I'm going to tell you about is research that shows that, interestingly, these neural networks that have been optimized for understanding also have good fits to the representations that we see in the brain, which suggests that whatever solutions the brain has, you know, settled on over the course of evolution and learning in order to do the stuff that it does, and much of what it does requires understanding, was a result of optimization for prediction. And that furthermore kind of emphasizes this claim. So what do I mean by prediction? Let's just get very clear on this, because it's key for the entire talk. The key thing for me here is the arrow of time. So, you know, you can take any data stream and you can use one component of the data to make an estimate of what you're going to see on the other components of the data. And you can then, you know, identify some error between your estimates and the actual data as it exists in the data stream. But by prediction, I specifically mean the case where you're doing this in the arrow of time. So you take some data points in the past and you use them to make a guess about what you're going to see in the future. So, you know, slightly more formally, we imagine that we have some stream of data over time, X, and that's being fed into a system which has internal states and can interact with the environment, whatever, it doesn't really matter. But that system is going to make some guess, some prediction about what it's going to see at the next time step. And the differences between that and the difference between that prediction and the data actually received is the error, effectively, that one would use to train such a system. So taking the past and using it to estimate the future. That's what I mean by prediction. And in the sort of real world sense, of course, that just means if you imagine, you know, you're watching things happen in the world. So you're an animal that sees this frog jumping. It would be about, okay, you know, if you see the frog get to this point in the air, that you can then make some estimates of this is what I'm going to see on my retina in the near future, the frog land on the ground. That is what I mean by prediction. So let's talk about optimizing for prediction in AI. So optimizing for prediction has become a key tool in AI systems in recent years. Probably the best example of this, which some of you are likely familiar with, is optimizing for prediction in large language models. So I'm not going to go into the technical details of how these language models work, but I'd happily do so if people are interested. But the way that they fundamentally work is actually pretty easy in the, like, when you actually just describe the task you set up for them and how you optimize them. So what they do is, so most of these models, I should say, are a new type of neural network architecture called a transformer net. Transformer nets are basically neural networks that have some additional attentional systems in them, or even one could say that are at their core attentional systems. And what they do to train these large language models, such as GPT from OpenAI, which you may have heard about, is they will feed in sentences taken from large internet corpuses. So they feed in sentences, and the neural network will receive as input all of the words up to a certain point in the sentence. So here we have the start token, and then the words not all heroes wear. This is the input sequence. Your neural network, which here GPT is just represented with this single box. It's of course much more complicated than that inside the box, but this is the simplification. Our neural network then has to put out a guess about what words it's going to see next. So, you know, maybe it'll guess that the next word with 90% probability is capes, with 5% probability pants, etc. And then what they do is they literally just take the output guesses and compare it to the actual next word in the sentence that the neural network received. And they calculate an error. So how close was the neural network's guess to the actual word received? You know, so if the actual word in the sentence was capes, there would be a very low error. If the actual word in the sentence was pants, there would be a medium error. And if the actual next word in the sentence was something so totally different, whatever, cowboy hats, then you'd have a high error. So you take that error, and then you just do backpropagation. You backpropagate on that error, and you update the synaptic parameters in your neural network to make it better at guessing the next word. And you do this many, many, many times over on a very large data set of language. And the result is a neural network system that is eerily capable of very coherent and cogent conversations, as well as surprisingly creative text generation and knowledge answering. Here's just an example. This is a very simple test. You can see more tests on this website. You know, so the cue here would be a question that a human being would ask of the neural network. So what would happen here in this test is you'd feed this sentence in, the question, so what is your favorite animal? And then the neural network literally just word by word, based on that prompt, engages in this task, except that now what it's doing is it's spitting out a new sentence. So it's producing its own new sentence based upon its own predictive language model. So A here is the answer. This is all generated by the neural network. So you give it the question, what is your favorite animal? My favorite animal is a dog. Why? Because dogs are loyal and friendly. What are two reasons that a dog might be in a bad mood? Two reasons that a dog might be in a bad mood, or if it is hungry, or if it is hot, and so on. This is all just achieved by training on this predictive task. That's it. And if you go through the answers, you can see there's all sorts of signs of something that one might be inclined to call understanding, and which I will straight up call some level of understanding. So for example, you know, are there any animals with 3 legs? No, there aren't any. Why don't animals have 3 legs? Animals don't have 3 legs because they would fall over. For me, that's pretty remarkable. It seems to understand the point of the question. It seems to understand, you know, what the question asker was ultimately driving at, and it seems to understand that, you know, there is this basic task for animals to stand up and that they need sufficient legs to do so. So you can even see this when you let the system do much kind of like more extended construction and just sort of generate its own stuff. Here's a really fun example where you give it a prompt and then you let it go nuts after your prompt. So the prompt given here was, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes. And what you can see from this answer is, you know, it's a remarkably kind of like cogent little fantasy that the neural network cooks up in response to this prompt. So the scientists named the population after its distinctive horn, Ovid's unicorn. Dr. Jorge Perez, an evolutionary biologist from the University of La Paz, and several companions were exploring the Andes Mountains when they found a small valley with no other animals or humans, etc. This is all just fantasy constructed by the neural network based on this initial prompt. And note also that it is exhibiting some interesting connections and associations here that I, again, would call understanding. It knows that if scientists are looking for unicorns in the Andes mountain, it's perfectly reasonable that those scientists would be evolutionary biologists from the University of La Paz. Now, no one told it that. It was just that it has this understanding of, you know, if there's scientists looking for animals and they're in the Andes mountains, it's a reasonable guess that maybe they'd be something like an evolutionary biologist from the University of La Paz. And you can see this, there's tons and tons of examples of this, and it's really surprising how well these large language models can engage in these sorts of both very clear, cogent kind of question and answering stuff, as well as cogent imagining, as it were. Now, of course, they're not perfect, let's be clear. So in fact, there's still many gaps in some of these language models. The interesting phenomenon this way is that people have found that if you just make these language models even bigger and bigger and bigger, they get better and better and better. But nonetheless, there's still some gaps. But those gaps themselves in the system's understanding can be revealed by the prediction task. So what you can do here is for example, we'll give it a sentence and you see whether or not it completes that sentence, predicts basically a word that looks appropriate. So, you know, he complained that after she kissed him, he couldn't get the red color off his face. He finally just asked her to stop wearing that what? So obviously a reasonable thing here, if you understand the sentence, is to say lipstick. A not so reasonable thing, if you don't understand the sentence, is to say bracelet. Now, most of the time, these language models trained in this prediction task will actually get this task, will accomplish these sort of fill-ins quite well, but occasionally they won't. So, you know, here's an example. So this is BERT. This is another large language model. Interestingly, it's not nearly as large as GPT. So GPT does better on these tasks than BERT. But my point here is that one of the ways we reveal the lack of understanding is still by testing the predictive capability. So this BERT system that wasn't as good as GPT, you know, this is a paper from Ettinger where what she did was actually applied sort of computational linguistics tasks to these models. You know, so this example, Pablo wanted to cut the lumber he had bought to make some shelves. He asked his neighbor if he could borrow her. So the system predicted car as its first choice. And obviously right off the bat, you're like, well, you didn't understand then, because, you know, why would he ask to borrow a car if he wanted to cut the lumber? He should be asking to borrow a saw, right? Most of us would recognize that because we understand the sentence. The point here is that we're revealing the lack of understanding that does exist in the AI, in part by showing that it doesn't actually make the right predictions. And so in fact, if we got better at training it on all these predictions, it would forever exhibit more and more something that looks like understanding. So my claim here is not that these systems exhibit perfect understanding, they don't, but my claim is that they exhibit partial understanding, and that part of how we get them to be better in terms of their understanding is in fact by getting them to be better at these sorts of predictions. Okay, so that's large language models. Let's also talk about predictions in other domains now. So another example where people have applied this to is predictions in visual processing. So this is from a paper, a recent-ish paper in computer vision, where they're using something called contrastive predictive coding. And you don't need to understand the technical details of it, but let me explain this diagram a little bit to you so that you can understand what's happening in these neural networks. So in this image, these gray squares here, these represent video frames. So this is, over time, you're feeding in groups of video frames from a movie, okay? It could be any movie you want. So you feed in 5 frames, and those 5 frames get fed into a neural network, represented here in this diagram. And that neural network will first process those 5 frames using a convolutional architecture. If you do neural networks, this is basically a 3D convnet. And then the output from that convolutional neural network will be fed into a recurrent neural network. And that recurrent neural network will use its recurrent connections to propagate activity forward through time. And what happens in this neural network is that the output from that recurrent neural network then gets fed into a memory system that can store memories of past events, where events are literally just past vectors of activity in these neural networks. And it uses its memory then to make a prediction about what it's going to see in the next set of frames. So from x at t, you get this representation from the convolutional neural network, which we call z at t. That's used to generate the prediction. That prediction we call z hat here. And so z hat at t plus 1 is compared to the actual z at t plus 1. And again, you calculate an error. How similar was z hat to z at t plus 1? And that error is used to then backpropagate and update all of the synaptic weights in this neural network. And part of what happens when you train these systems is that they develop internal visual representations that make the system much better at learning other downstream visual tasks now. In part because I would argue they have developed some understanding of the structure of the visual world. So here's a specific example of that from this paper. So they apply this to a data set here called the UCF 101 data set. This is a big data set of movies of people engaged in different actions. And in this case, the data set is labeled with the name of the actions. So, baby crawling, rope climbing, salsa spin, whatever. And you can then give the neural network a task. You can say, okay, with these action movies, now tell me what actions the people are engaging in. So there's a label, which is the action name, and you have to classify the action based upon the video. That's the task for the neural network. And what's interesting is that if you do this predictive learning first, so you don't do the supervised learning first, you just do the predictive learning. You just say, in an unsupervised fashion, predict upcoming visual information, correct yourself based upon the differences, the errors between your prediction and reality. What you end up getting are representations that then make the neural network much better at then learning this supervised task. So if you then give the neural network, only 10% of the original labeled data, you can immediately get up to 45% accuracy on classifying these different actions. So here in light blue, we have the curve that you get if you're just training the neural network from scratch in the supervised task. And in dark blue, we have what happens if you train the neural network after it's done some of this predictive learning. And so my claim is precisely that the reason that we have this performance improvement in the downstream supervised task after having done this predictive learning is because part of what it's done is it's learned representations that help it to form something like an understanding of how objects move in the world. And that understanding of how objects move in the world is then sufficient for the system to engage in this supervised learning task of classifying what actions it's looking at. Okay, So let's also look at this in a reinforcement learning case. So here we have an illustration of a neural network that's doing reinforcement learning. And let's simplify this a bit. I didn't want to bother erasing all of the variable names, but we don't need to pay attention to all of those. Let's just focus on what's key. This is from a paper from DeepMind from a couple of years back. So basically they have their representation of the world. And so this is typically with these agents, the world is some three-dimensional environment. So it's moving through a sort of virtual reality or a video game, if you will, like a first-person shooter kind of perspective. So it has a camera that moves through this 3D world, and the agent can take actions, move in particular directions, different things, etc. So we've got some world that we're going to feed into a neural network, and that neural network is then going to determine some behavioral policy. So basically just, given the frames that I'm looking at right now, given the particular world I see, what action am I going to select? Am I going to move forward, move backward? Am I going to pick something up, etc.? And the goal here, of course, is to engage in behaviors that allow the system to maximize the rewards that it receives, where the rewards will be defined by the modeler at some point. Now, in this particular original version, what we've got here is a fairly simple neural network. This is a long short-term memory, so LSTM. So this is a reinforcement learning LSTM. So the way in which it determines its behavior is simply using a recurrent neural network, basically, that gets maximized, that gets trained, again, via backpropagation to maximize its rewards. Now, there's an alternative architecture that some people had proposed in the mid-2010s, which is what we call a memory augmented architecture, RLMem here. It's very similar, except that, so we've got our world that we're feeding in, and then we've got a neural network that's determining our behavioral policy, but now our neural network has a memory system, a long-term memory system. So it not only has the recurrent connections for a sort of working memory, but it also has a long-term memory system where it can write memories to a memory bank, store them for long periods of time, and then recall them when it needs to in order to determine its behavior. And these systems can exhibit more sophisticated reinforcement learning than these systems here. But in this paper that I'm talking to you about right now from 2018, what they did is they introduced this new system that they called Merlin, where they beefed up the memory system by quite a bit by making it a predictive memory system. So they had still their world, they had still their behavioral system, but now what they had here is this memory system where the memories that get stored are not just whatever happened to the agent, but they're actually memories that are optimized, again, via backpropagation, to allow the system to better predict what it's going to see in the near future using its memories. So basically, it recalls a memory at every time step. It takes that recalled memory and compares it to the actual data received, and it will then update its own mnemonic parameters and change the sort of memory that it has for the past based upon how well it ended up predicting the future. So it becomes a sort of malleable memory that is actually optimized for predicting the future. And what's interesting, what they show in this paper is that by taking this predictive memory approach, the system is able to develop what I would call a better understanding of the environments in which it lives in order to accomplish more difficult tasks. So here's one relatively clear example. So they put the system in this large maze environment, and they would give it different goals, like, okay, go to this room, go to that room, go to this room, go to that room, etc. And it will receive rewards for achieving the goal location. But the room is sufficiently large, this maze is sufficiently large that, it takes a number of time steps, so the rewards aren't immediate. And also the agent can't see everywhere throughout the entire maze. It needs to actually navigate to unseen areas. And what's interesting about what happens when you include this predictive memory system is that part of what the agent is then able to do is it's able to, as it's moving through the environment, get much better at predicting when it's approaching somewhere that is ultimately good for it. So here we're looking at the return prediction value. So this is the agent trying to predict how much reward it's going to receive in the future. And as the agent moves through this path, so this is the agent's path, and the color indicates its estimated return. We can see that it starts to get an inkling throughout here that it's going to get some reward. But of course, that is not because it can see the reward location. It can't. So it's not just that it sees a rewarding stimulus. It's not just a stimulus response thing. It's not some behaviorist system, right? Instead, it has an internal map of the environment. And it knows that in this particular location, it is closer now to its goal than at this location. And so its estimate of its return increases. And that's courtesy in part of its ability to form predictions based on its memory. Because it remembers being in this part before, and it remembers that it took this route previously to get to the goal location. And you can train these agents and drop them in any part of the environment, and it will navigate to different goal locations, and it does so in a very robust way that indicates that it truly does have an understanding of the spatial structure of the maze. And that then can also be exhibited by its actual performance. So here we're comparing to the other two systems that I showed you on the last slide, RL-LSTM and RL-MEM. And these reinforcement learning systems, which are optimized to maximize reward, and which have memory in the case of the RL memory system, they don't actually do this task well because they don't understand the structure of the environment fully. In contrast, the predictive memory agent does. It has formed an understanding of the spatial layout of the environment, and so its time to reach the goal drastically drops within a sub-episode as it is exploring the environment. So sub-episodes here, I should say, is like you give it a new maze and then you let it explore that maze. So what's happening in this curve here is that it's it developing its understanding of the spatial structure of the environment. So my take-home message from this first part is basically that training AI systems by optimizing them for prediction produces systems that exhibit better understanding and faster learning. By faster learning, I mean with fewer labels and rewards. And then of course, all of that is done without labels and rewards. That predictive training is unsupervised. There is no explicit signal given other than the sensory data itself, which serves as the target. It's what we actually call self-supervised learning in AI nowadays.
Can I ask you a question?
Sure.
Is this, could you go back one to that message, take-home message?
Yeah.
Is there more to the take-home message than that it's better for learning to unpack parallel supervised learning type learning where everything's happening, but it isn't separated into sequential steps that can improve, to separating it into temporal sequential steps that can improve? In other words, reinforcement learning itself.
I'm sorry, I don't understand your question. So what is the thing you mean by sequential, separating it into sequential steps?
It's a series of steps, and steps allow you to make a prediction about what the next step is.
Mm-hmm.
I mean, that's clear. I mean, I think without any strong brief for prediction being the underlying factor in all of this, you would say that yes, a serial sequential way of doing things is more amenable to improvement, successive improvement, than a parallel one.
So what do you mean by a parallel one? Can I ask you?
Oh, okay. Standard backprop where you take ordinary supervised learning, where you take a whole bunch of cases and their supervised outcome and just whip them through, rather than go from one to the other step by step.
Oh, I see. So the answer is no, it's not necessarily the case that that's the distinction, because in fact, to be clear, sometimes what they're doing in these systems is still batched training. So here, for example, what they do is when you actually calculate this error, you'll take a bunch of movies and you'll run a bunch of movies through your neural network at once and calculate multiple errors and then do an update to the batch. Now, it's true that the data itself has a temporal structure. So here's maybe the other component to your question, which is that I think that, actually, that's not the direction I wanted to go in. I think that if you think of, if we think about the nature of a data set that has time to it versus a data set that doesn't have time to it, a data set with time has so much more information in it. If I give you just snapshots of a frog and I try to train you on recognizing a frog, at best, what you're going to be able to do is extract the sort of features that tend to correlate with the label frog. But you're not necessarily going to develop anything like an understanding of how a frog moves through the world, how it jumps, you know, where it tends to move to, what it tends to move away from. None of that can be part of your understanding. To get that, you need a temporal stream of information. You need something where you can see the frog moving, where you can see how its legs operate when it jumps, where you can see what was present when it jumped away from something, etc. So I think if I understand your correction fully, then yes, a very kind of like implicit and importantly implicit component of my claim here is that part of what we want to develop understanding are data streams with time, because that's key to understanding the real world, because the real world exists as something in time. And just giving little snapshots like individual images is not going to be enough typically to develop anything like a robust understanding. It'll allow you to develop some understanding, say, of which features tend to correlate with which categories and stuff like that, but that's it.
Okay, thanks. That may or may not come up again later, but thanks.
Sure. Are there any other questions before I move to the next section?
I don't see anything in chat, but maybe I'll encourage people to put stuff into chat if you're planning to ask something, and then I can signal Blake. Go ahead.
Yeah, and do feel free to ask questions in French as well. Totally fine. Okay, so optimizing for prediction in the brain. So the next thing I'm going to show you are results that show that when we optimize these neural networks to engage in prediction, we end up getting representations that match the real brain better than other models. And that's, I think, really fascinating. So here, let's think about this, breaking it down this way. So this lovely paper from Cocheteau and King from Facebook, what they laid out here is, okay, when we're thinking about these neural network models, so we train a neural network model to engage in this sort of prediction. And then we can ask, if we compare the neural network's representations to the representations in the brain, and we ask how similar are those representations, which of the following scenarios are going to hold? So is it going to be the case that neural networks that are better at these prediction tasks match the brain better? So that's what brain score here indicates. 0 indicates you're not matching the brain at all. 1 indicates a perfect match to the brain. Is it going to be the case that we have, like, as we improve our accuracy on these prediction tasks, that we're going to get a better match to the brain? Is it simply going to be, you know, that there is no relationship? Or might there even be a divergent relationship? Perhaps the better we get at prediction with a language model, the less it will match the brain. And what we might argue is that, you know, in the case where you have divergence, that shows you that the brain was probably not optimized for this task. Because if getting better at this task leads to divergence from the brain, then that does not suggest that the brain's representations were in any way a solution to this task. It's the opposite for convergence. The better, if it is the case that the better the performance of the model on language prediction accuracy is, the better your match to the brain, that suggests that indeed the representations in the brain may in fact be a result of an optimization process for this prediction system, for this prediction task, as it were. So the way they do this in this study is they collected fMRI and MEG data from 195 subjects. And they can then take the activity that they see in the brain with these two techniques, and they can ask, to what extent can we then kind of match, literally just through linear regression, the representations that exist in a neural network to the representations that exist in the brain. So what they'll do is they'll feed in the words into the neural network. So dogs chase cats. Again, the neural network is trained to predict upcoming words. So, you know, it will predict dog, say it predicts R for dogs. So that's where it had an inaccurate prediction, because the actual sentence was dogs chase cats. So dogs are wrong prediction, chase cats it predicts, that's correct, cats was coming up, etc. But the way that it's forming this prediction is by propagating activity through the neural network. And so that's what's represented with these squares here. This is supposed to be activity from the neural network. And the thing is, you can take this activity from the neural network and you can not only predict the word, but you can then literally ask, if I take this activity and I try to do a linear regression from this activity to the activity that I got in the fMRI scanner or the MEG scanner, how well can I match that? And what that tells you, to be clear, is if you have a high match, if through just a linear regression from your neural network to the neural data, you can get a reasonably high R squared, that tells you that the structure of the representations in the neural network were just, their difference from the real brain's representations was one just of a linear transformation, suggesting that the overall structure of the representations in high dimensional space are the same. And what's ultimately different is just that they're being, you know, twisted and stretched and scaled, etc. Okay, so that's what they do in this study. So then they're going to measure the R squared between their predictions from the neural network activations of brain activity, and they're going to compare that to the accuracy of the models in the predictive task. So first of all, they just compare across the different layers of the neural network, where do they get the best R squareds for different parts of the brain. And one of the things that they report, these two, the causal versus masked, I won't bother explaining, but the causal is actually the most relevant one. This is where you're really trying to predict the next word in your neural network. What they find is that in the middle layers of the neural network, illustrated with these red bars here, that's where they get the best correlation to the signals from the fMRI system. The bottom here, this is just the word embeddings. So this is literally just kind of like information about what word was being observed. And you can also, like it's a vectorized version of what word was being observed. And you can also perform that same regression analysis from the word embeddings to the brain data. But what you can see is you're not very good at doing that. So if you simply know which words the person's looking at, because I should have said, the people were reading these same sentences that the neural network was being fed. That's part of how you do this. So you give the person the same sentence you fed the neural network to give those activities, and then you perform this regression. And what we can observe is that basically when people are processing these sentences, if you simply take knowledge of which words were being presented and try to predict their brain activity, you don't do very well. And indeed, it's also hard to predict the next word. Your accuracy here on predicting the next word is not always as good. Although, let's just say this is, this is for different neural networks. So each dot here represents a different neural network that has been trained on this task. And this is their word embedding level. But then in the middle layers, what we see is this fascinating thing that as the neural networks get better, so this is, their performance over time, as their performance gets better, we get better and better fits to the neural network, to the real neural representations. There's some limit to this. So at some point in accuracy, you're no longer getting improvement, which they've highlighted with the gray square here, the dotted dashed line. But nonetheless, there's this very clear relationship. And this holds both for fMRI and MEG. As you increase your accuracy on predicting the next word, which is what the x-axis is here, you get better and better R's relative to your MEG data. And furthermore, what's interesting is that when you map this onto the brain and you look at where you're getting your highest similarities, so where are you best able to explain your neural representations, depending upon which components of the neural network you use or which model you use, it maps onto different parts of the brain. So if you, here what they've done on the top is they've trained a neural network just to recognize words, like literally read words. So, you know, you give it an image of a word and it says what word it's looking at. If you train a neural network on that task, you can predict some brain activity, but only in primary visual cortex and a bit of some higher order visual cortex regions, but basically in visual cortex. So the neural network that's been trained simply to recognize words will show some similarity in its representational structures to the real brain's visual cortex, but that's it. It doesn't have anything like the representations that support language processing. When you look at the word embeddings themselves, you do get some fits to higher order areas, but it's even more striking when you look at those compositional middle layers. So the parts of the neural network that were key for it developing its predictions. And here now you see really nice fits to various parts of the superior temporal lobes, prefrontal cortex, various parts of the brain that we classically associate with semantic and syntactic processing, as well as higher order thought processes. And that suggests that whatever representations are supporting those processes in the brain are actually best explained, or not best explained, let me say, can be partially explained by suggesting that those representations in the brain were the result of optimizing for prediction. Okay, so then we can see a similar thing with visual tasks as well, actually. So this is a study from my lab now that just came out in NeurIPS. Basically, one of the things we were interested here is that in the real brain, we have these two different forms of representations that we see, the what and where pathways, or the dorsal and ventral pathways. So we have along the top of our brain, this dorsal pathway that is concerned with where are things and where are they moving to, and this ventral pathway that's concerned with what things are there and what do they mean. So we've got these two different forms of representations that support two different forms of understanding. And indeed, if you lesion these different pathways, a person with a lesion to the dorsal pathway will have trouble identifying movement and grasping objects. A person with a lesion to the ventral pathway will have difficulty identifying objects and recognizing their meaning. And so part of what we kind of thought about with respect to the prediction of visual inputs here is that we think that what and where distinction, the dorsal ventral distinction, might actually map on to two different components of the prediction task for vision. And specifically, if you think of an object, like you're watching some object moving. So let's say you see a car and it's moving to the left. There are two different things that you can do in terms of your prediction. The first is that you can make a movement invariant prediction. You can say, I will see an orange car in the near future, because as long as it's not moving at some exorbitant speed, you're still going to see the orange car in your visual field in the near future, even if it's moving. And so regardless of whether it's moving or where it's moving, you can make this movement invariant prediction. I will see an orange car. Similarly, you can make some predictions about movement that are invariant to the specific object identity. So regardless of whether it's an orange car or a dog or a bicycle, if there's an object moving to the left, you can be sure that you're going to see some leftward movement in your visual field. And so it's an object invariant prediction regarding movement. And what we hypothesized in this paper was that basically if you therefore optimize a neural network for visual prediction, you're going to get out what and where, or dorsal and ventral pathways from your neural network, simply because there are these two different forms of understanding of invariance that are required to do this task. Now, we studied this in mice, in this case, because that's the sort of data we tend to work with, is invasive recordings in animals, but mice also have what we might call dorsal versus ventral pathways. So Here we're looking at 5 different brain regions in mouse visual cortex that have different scores for how dorsal or ventral they are. And we can also look at the similarity in the representations between those 2 regions, or between these 5 regions. We can see that, so this is comparisons across mice of the similarity in their representations. This stands for representational similarity matrix. And basically this is a measure of how similar are the representational geometries in 2 animals across different regions. And we can see that indeed, animals tend to be consistent within different brain regions in comparison to each other. So we're measuring something real here. This is sort of a sanity check as well. And then we can ask across these different regions, from more ventral, that is more of a what pathway, to more dorsal, more of a where pathway, do we see a neural network that's optimized for prediction match all of these regions? And the answer is yes, we do. So here what we do is we take a neural network, we then have 2 separate anatomical pathways, and the neural network just tries to predict upcoming stimuli. So we train it off of videos, just like that previous neural network that I showed you in the earlier part, where it's taking in video frames and it's trying to predict the next video frames it's going to see. If we train the neural network with that, and we give it these 2 distinct anatomical pathways, what we're showing here now is the similarity, as in the last paper I showed you, to the neural representations that we observe in mouse cortex. And what we find is that, if we compare it to an untrained neural network, so here we've got an untrained neural network similarity. Here we have a network that has only 1 pathway, so it's incapable of forming separate representational specializations in the same way. And here we have a neural network with 2 pathways. We can get the best similarity to all of the brain areas when we train this network with this predictive task, and it has these 2 separate pathways. And what's interesting is that what we find, so not only does it match all of the areas, both the more ventral and the more dorsal, when we also then test this neural network on downstream tasks. So we give it both an object categorization task here from the CFAR10 data set. So we give it different images and it has to identify what category of image it's looking at. Or alternatively, we give it a motion discrimination task where there's a bunch of random dots moving in different directions with different degrees of coherence, and it has to say which direction the dots are moving in. Some of them are moving randomly, but some subset are moving coherently. This is called a random dot kinetogram test, and it's a very common test for studying regions like MT and in the primate brain. We selected these 2 tasks because they map onto the what and where pathways in terms of their specialization. A person with lesions to the ventral pathway will have trouble with this sort of object categorization task. As well, if they're doing this kind of task, you'll see ventral regions light up. Whereas a person with lesions to the dorsal pathway will show problems with this sort of motion discrimination task. And likewise, that part of the brain will be active when they're doing this sort of task. And what we find then is that if we take our neural network with these 2 paths, and the neural network's been optimized on video prediction, and then we freeze the representations, we say, okay, we're not going to do any more training, and now we're just going to do a linear regression off of those representations to perform these 2 tasks. What we find is that in our ventral-like pathway, we do better on our object categorization task. And in our dorsal-like pathway, we do better on the motion discrimination task, showing that indeed the representations that have been formed are actually related to this sort of what versus where specialization. So if you optimize a neural network to do prediction, you also get representations that map onto this interesting specialization that we see in visual cortex. Okay, and then finally, and actually I need to wrap up, predictive networks also match, interestingly, representations seen in memory and navigation circuits. So if you have a neural network that's doing something kind of akin to, this is a lovely paper from James Whittington and Tim Barron's lab. If you have a neural network that's kind of trying to do that same sort of memory prediction thing I mentioned, so it's using its memories to predict what it's going to see in the future, and you have it move through some world or through some set of relationships, and you use this memory system that here they're equating to the hippocampus to engage in your sensory prediction, the result is that you get representations that look like what you see in the mnemonic systems of the brain. So I'll just run very quickly through this. Maybe I'll ignore their model and just say, here's an example of the sort of representations they see. So they end up getting neurons in their neural network that exhibit grid-like structures, which is exactly what you see in the entorhinal cortex. They also get neurons in their neural network that show clear place cell structures that remap in different environments, which again is exactly what you see in the animals. Here you've got data from the neural network, and here's actually data from a rat moving in two different environments. And you see the same sort of place cell activity, you see the same sort of grid cell activity that you get in real animals, etc. All simply from training the system to predict upcoming stuff using its memory. Okay. So my take-home message here is that neural networks that have been optimized for prediction match the representations observed in the brain surprisingly well. And so I think actually what I'll maybe do, because I know we've got a lot of time set out for discussion, and the last slides I had were actually in anticipation of some of the discussion we might have. I will actually cap off here for now and let us move into questions and discussion, because it's possible that some of what I want to say next will emerge naturally. And if it doesn't, that's also okay, because I'm already at my 50-minute time limit here. So yeah, let's move into questions now. Thanks very much for listening so far. I'll just, here I'll jump to, well, let me wrap up with this statement. So the first observation I gave you was that prediction is helpful for engineering AI that exhibits better understanding. And the second observation I gave you is that prediction is helpful for modeling representations in the mammalian brain. And so this is, what ultimately leads me to my broad strokes claim, that understanding is a property of systems that have been optimized to engage in prediction. And that's exactly what I think our brains are, in large part. I think our brains do other things. I'm not like Carl Friston, who thinks this is a theory of everything, to be clear. But I do think it's nonetheless very clearly one of the things that has shaped the development of the brain over evolution and probably during early development as well. Okay, so that's my claims. Let's shift over now. Any questions or comments?
Thanks very much. Go ahead, Jonas.
Yeah, my question is, you mentioned before that the time component is pretty critical in the model presented, and that allows the system to better predict, especially when it comes to object moving. Is there any, so let's just pretend that that time component is out of the equation, and we're just going by a system that try to predict, but really on a what. So, for example, in a convolution system where, the system is trying to predict or trying to name an object that he sees based on what he was trained on. If we take off the time component, is there any sign in the results that shows that maybe the system may have a little bit of understanding of that component of time based on the data that is provided to him, and how close, for example, like if you show him a cat in different states, is there any sign that shows that the system may have a little understanding of the time aspect based on the differences between the vectors of images, for example?
So I think that if you never actually provide the inputs in an ordered fashion, mm-hmm. and you never actually provide any signal, I'm sorry, is this my, I'll just say, is this my Slack? Apologies for all the notifications coming up. It's, there's a grant due and people are, Anyway, yes, so if you take all the temporal information out, so mm-hmm. you don't give it a sequence, and you don't even give it a label that says this was this time frame, this was this time frame, or anything like that, yeah, I think it's not going to develop the same level of understanding of many components of the system, of the world. Because, here's the thing to really think about with all of these neural networks. they always learn whatever they need to in order to minimize the loss that you've given them, minimize the error that you've specified for them. And so in the case of, objects where you just give it an object image and you run it through a convnet and then you say, okay, what category is this? One of the things that people have observed is that what these networks tend to discover is that certain textures are good for, let's say, predicting. I mean, like I said, I wanted to reserve the word predicting for predicting through time, but let's just use it for a moment here. Certain textures are good for predicting what the category of an object is. And so lo and behold, these networks rely a lot on texture for how they classify images, because that's the thing that was available to them. Now, I think one of the things that's worth emphasizing there, though, is that is because of the nature of the task we set up for them. All we did was give them static images and say, tell us the category. And the texture is informative for the category. So that's what the neural network discovered. We didn't give it anything else it could really use. For example, one of the things that has been observed is that the human brain tends to use shape a lot more. Well, I would argue that that's because, we, in moving through a world where we're trying to predict the sensory data we're going to see, including sensory data that results from us moving around objects in 3D, is that we're going to have to develop an understanding of shape necessarily as a result of that predictive task that includes time as a component and includes three-dimensional space as a component. And with those things in place, you then, when you're solving the task for prediction, end up learning about the nature of shape. And so now when I ask you to categorize objects, what are you going to do? You're going to use shape, because that's what you've developed an understanding of. So indeed, I think that temporal component is key. That is part of the point, is that the way that our understanding exists is a result of that temporal sequence that we receive in our lives. The arrow of time is critical to understanding human understanding.
Okay, thank you.
Yeah.
Other questions, or else I'll chime in. Munir, I know you came late, but you're entitled.
The problem is I didn't follow the methodology. So I noticed that there's a lot of statistical testing done, but I don't know the details of it. So usually I'm not very optimistic about truth coming out of statistical tests, but that's all I can say, really.
Okay, I mean, I'm not really sure how to respond to that. I'd be happy to give you more clarity about what these...
The thing is, it happens that this week I'm teaching Bayesian inference, and one of the things I tell my students is don't trust frequentists when they tell you truths about confidence levels and things of that sort. But then again, I really don't know the details of what you did, so I cannot really objectively, agree or disagree or have questions. Mainly because I thought the talks would start at 10:30, and apparently it started earlier.
I'm really sorry about that, Munir. They start at 10 now. Last semester they were 10:30.
Yeah, that's fine.
Well, here, one thing I can say though is the following, okay? So let me be clear. We were not doing any significance testing here. That's not part of the study.
You did a regression, right?
We did a regression.
Yeah. Yeah, that's, to me, that's classical thinking.
Well, except that the point is that what we're not doing with that regression is we're not then forming a null hypothesis and then calculating a p-value that tells us the probability of the data under the null hypothesis and using that to reject the null hypothesis.
Okay.
All we're doing is we're saying when we do a regression from neural network representations to representations in the brain, we see better fits, we see better regressions when those neural networks have been trained on a predictive task than when we don't do that.
I got you. Oh yeah, I can see here. In fact, the slide that you're showing shows box plots, right, of your results. Is that what these are?
Yes. So here we're looking at the RSM similarity. So this is basically a measure of how well you can. I mean, we can go more into the details if you want.
Yeah, okay, I get it. But you could see a significant difference with, despite the spread of the values that you're getting.
Yes.
Yeah, that looks interesting actually.
And it was a similar thing in the other paper I discussed here. So again, they're reporting R squared. They're reporting R values here, but their point is not that these R values are significant or not. The point is that there's a correlation between the R values that you get and the performance of the neural network on the predictive task. So, like without having to say anything about rejecting a null hypothesis, the claim is simply that what we see repeatedly, and you can see this is across many different random seeds. That's what each one of these lines here are. So across many different random seeds, the same pattern holds again and again and again and again, which is that the better the neural network is at doing the prediction, the better its representations can be regressed against brain data.
The final results. And there seems to be a dip in the relationship somewhere in the middle of the x-axis.
Here, you mean?
Yeah.
Yes.
Is there a reason for that? I mean,
Maybe.
is there an explanation?
That's a good question. They do not cover that in this paper, and I don't know that I have a reason for it that I could articulate. But it does seem to be there in this plot. I agree. It's maybe it's a little bit here in the MEG data as well, actually. Yeah, which is interesting. So there's like a sort of funny valley that the system goes through as it's learning, where it gets a little bit worse at matching the representations in the brain before it starts to get better.
Right. So that there was no attempt to link that to some kind of fMRI activity or something.
Not to my knowledge, no. I don't recall them trying to do that in this paper. The fact is, this fMRI and MEG data is very noisy, so there could be a lot of potential reasons for that. But yeah, that's an interesting point.
Okay, let me try to introduce a couple of fundamental questions. Sure. Nobody can quarrel. In fact, we can only agree that prediction is important. It's important in science. It's important that the brain should be able to predict. It's important that people should be able to predict. Nobody can quarrel with that. But my question is that too general? Take, for example, the predictive success of GPT-3 that you started out with. Yep. This will also perk Munir's interest. My first question to you is this: if we get too enthusiastic about the predictive function of GPT-3 and its success and its implications for the brain, are we just gonna face an equivalent of the frame problem on that too?
Well,
turn out to the predictions will, yes, they'll be partial and they'll be getting better and better and better, but in the end we realize that they're not understanding at all.
So no, my assertion would be I don't think that's the case, because
that's on the strength of your notion of partial understanding.
So indeed, I would argue that let's maybe start to unpack this. So my claim would be that it is, if you see the system exhibit what I would call partial understanding, you're making your way towards what we might call full understanding. Part of why I say that is that I don't think most humans exhibit full understanding. We all have some degree of partial understanding, in fact. And in this way, so this actually gets to what maybe I wanted to, what I had as saved for the last bit of my talk. So let's go here, because this is a cognitive science seminar series after all. So we might as well get into the thick of this type of question. Okay, so is any of this understanding? That's sort of the elephant in the room when I present these ideas to a more cognitive science audience. So, this is at the risk of being a cliche of someone who went to Oxford. I personally think that the only way to actually get at the question of what understanding is simply to look at how we use the word. So, when we say, is this understanding, what we're really asking is, does this situation fit the contexts in which we use the word understanding? And so, as Wittgenstein argued, I think that for most words, we basically just have to look at the context of its use and decide whether or not that word is appropriate there. And so, necessarily we have to have a way of judging the correctness of that use. And that's the key question. Can we judge the correctness of the use of understanding here? And I would argue that in the case of partial understanding, as with these neural networks, what we can do is we can say, yeah, like we all have an inclination to use the word understanding in a situation where we're having a conversation with GPT-3, and it's most of the time producing perfectly sensible responses to us. Just as we do with a person who exhibits most of the time perfectly sensible responses to us. And I don't think that there's some, ontological distinction between a system that understands and a system that doesn't understand. The only thing there is the question of whether or not we would apply the use of, whether we would use the word understanding in these circumstances. And so as far as I'm concerned, I think, yeah, it's understanding. I don't think you could have a system that exhibits all these behaviors, which you then say, this system doesn't understand.
Let me take a crack at that. I don't think it's an ontological distinction, but something that would produce the thing that you don't think exists.
Yes.
And it'll be with a relatively old example, but you've already opened the door to it by talking about Wittgenstein and use and things like that. Ha elkezdek most magyarul beszélni, akkor egy szót se fogsz érteni. I assume that I'm not mistaken that you had complete non-understanding of what I just said.
Correct.
Okay, because it was in Hungarian. Okay. Whereas when I speak now, et puis si je parle français, c'est peut-être partiel, mais tu comprends quand même.
Oui, je comprends bien.
Okay, so there's a distinction there. And I think it's exactly that distinction, although it hasn't been frequently acknowledged, that Searle was using in his Chinese room argument. He said, look, his boogeyman was not a prediction model, but a Turing test passing a symbol manipulator. He said, it's not understanding. And because when I do what it's doing, I'm not understanding. There's something missing. That was his argument against sort of symbol manipulation as being the embodiment of understanding. But what he used was a criterion that's the same criterion as I just used now. And by full understanding, we don't mean understanding error-free understanding or GPT reaching error-free prediction and performance. We mean something else, and it's there when you understand, and it's not there when you don't understand.
So I have a very
I figured you would.
I thought that this might come up. And my answer is, I have always considered the Chinese room argument to be possibly one of the most incoherent and unhelpful arguments that's ever been presented in cognitive science. And the reason is precisely because what Searle does in this situation is he sets up a situation where someone outside of the room who doesn't know what's going on inside of the room will use the word understanding. So if you do exactly what that test you just did to me, and these people standing outside of the room receive back the messages, they're going to say, whatever's going on in there, it understands this sentence. So they would use the word in this context. Now, but what Searle's done is he set up this funny situation, this slightly silly situation, where then those of us who know what's going on inside of the room want to say there is no understanding there. But in doing so, he's made it impossible to apply the word understanding to this context. In other words, there are no rules for usage here that can apply to this situation because of the way Searle set it up. And as a result, per Wittgenstein's point, the word understand is meaningless in the Chinese room. He's just flapping his lips as far as I'm concerned.
But isn't it part of intelligence? Because if you look at GPT-3, it's doing exactly what this Chinese room metaphor is saying. I argue that GPT-3 doesn't have the faintest idea about what it's doing. And this has been acknowledged by its authors. You know, I mean, they had this experiment where they trained the network to do additions with 3-digit numbers. And then when they tried to have it do 6-digit additions, it failed miserably. So it could not understand that it was doing additions.
But there's the point, right? So why do the authors say, yes, it doesn't really understand what's going on here, or it doesn't fully understand? The reason they say that is precisely because, unlike in the Chinese room argument, there were certain inputs to the system that led to the wrong outputs from the system. There were, like, literally there was a situation where you gave it these symbols, and then the symbols it spit out were not the right ones according to the rules of the language and the rules of mathematics. And that's why we say it doesn't understand. It's not because we say, well, it's just following rules, so therefore it doesn't understand. That's not the argument. The argument is, look, we show that its behavioral competence is not equal to that of a human being. And of course, the critical thing for the Chinese room argument is that this is somehow is equivalent to the competence of a real human being. Because of course, if these people outside of the room were able to give some inputs to Searle in the room, such that he gave the wrong outputs, then they would say, no, it doesn't understand. But that would be equivalent to the situation with GPT-3. Right?
Well, it may be that you could do the whatever task you're doing without need of understanding what you're doing. In fact, algorithms like GPT-3 prove that understanding is not necessary.
No,
to do something.
I totally reject that. What I'm saying is that understanding is whatever we would apply the word understand to. And so if the situation that you have is such that GPT-3 is always giving you the right sort of outputs, we would apply the word understanding, just as the people inside.
But it's not. That's what I'm saying. It will give you the right output on the data that it was trained on. But if you try to use this, the meta-learning capability of intelligent beings, it doesn't have that capability, in the sense that in the example of the addition, it can add 3-digit numbers because it was trained on that. But if I give it 6-digit numbers, it's not capable of understanding that actually adding numbers that have 3 digits is no different from adding numbers that have 6 digits. The operation that is being performed is the same for both. But in the case of GPT-3, it was trained on 3-digit additions, and it learned to do that.
Yes.
But when somebody gave it a different number of digits to add, it could not, because it did not understand what an addition is. It was doing mappings, essentially.
I understand. Well, no. Okay, so hold on. You see, your last thing there is the problematic point. So what you're doing here is, again, you're adding new tests. You're taking whatever existing Turing-ish test we have for the system, and then you're adding new criteria. You're saying, now I'm not just going to test you on 3-digit numbers, I'm also going to test you on 6-digit numbers. And lo and behold, it now fails your expanded Turing test. And that's why you say it doesn't understand.
Well,
My
did you
claim is
understand
that
the task of adding?
if there is no additional task that you could add that wouldn't reveal a lack of understanding, then we would have to call it understanding. Otherwise, the word understand is meaningless. There is no such thing as understanding other than exhibiting all the behavioral competences of understanding. But that's what it is to understand. That is when the word applies.
Yeah, but take a kid that is learning addition. How do they learn addition? They learn it by the rules of addition, right?
But
I
how
mean,
do they learn
they end up figuring out that whether they're adding 2 numbers or 3 numbers or 6 numbers or whatever numbers there are, this is how they'll do it, right? Here, what we're doing is we're giving a bunch of examples to a neural net. We're saying, hey, do a gradient descent, minimize, you know, the loss function that you have, whatever it is that you defined as a loss function.
That's what we do with kids.
And in the end, you know, the system will tell you, hey, listen, this thing looks like that stuff I saw before. So I'm gonna give you the answer.
But that's what we do with kids. That's it. Like when a kid learns to do mathematics, you can't magically give them understanding. Instead, you show them examples. And you run through the examples with them. You show them, okay, here's 2 things and here's 3 things, and then together I'm going to call this 5. And you do this repeatedly with them. And through that, they develop an understanding. That's it. It's the same process. It's just that human brains are a lot more sophisticated.
But you just said it. They develop an understanding. Here I have GPT-3, which costs $12 million each time you run it on a training task.
Yeah.
Okay. Which has 175 billion parameters to train, if I recall, and which was trained, by the way, on 6 trillion words.
Yes.
Or examples. Okay.
But let me clarify one thing before you continue.
It cannot figure out what an addition is.
No, so let's clarify something, okay?
Yeah.
So first of all, I'm not claiming that GPT-3 is a perfect model of the human brain. I want to get very clear on that. Like, that is not my claim by any means. We can point to so many differences between GPT-3 and the human brain. We could go on and on and on pointing that out. The claim that I'm making is that when we look at how human beings develop understanding, it's not radically different from simply being given examples and using those examples to extract some solution to this problem, which then is that solution is basically what gives us understanding. It is what an understanding is. It's when we have that solution that we apply the word understanding, that we use the word understanding.
Yes.
So if you look at a child, right, like you just said, a kid understands the rule. But here, I'm going to ask you a question. Assuming you've had kids, did you try asking your kid maybe who first learned how to add numbers under 10 to add numbers over 100? They can't do it all of a sudden. They don't all of a sudden magically have some rule that applies universally in all contexts. Rather, they know how to do those things that you've gone over with them, which is how to add numbers under 10. And so their understanding is partial. My daughter is at the point where she can add any numbers of 2 digits, but she can't add 3-digit numbers. She can't add 4-digit numbers. She'll get there, but she's going to get there through examples, through training. There is no magic understanding that she has received as a result of my interactions with her. What she's done is she's learned how to produce the right outputs given the particular equation strings. And it's
I agree with you.
not fundamentally different.
Yes, we learn to do something, but that does not necessarily mean that we understand what we're doing. Let me give you another example, okay? You're familiar with the story of the game of Go, okay?
The game of Go.
How a program was developed to beat the world champion.
Yes.
Okay. There is a little news that went unnoticed. It's the fact that actually that algorithm also defeated the previous algorithm that was the world champion at playing chess. Okay, so you're aware of Deep Blue, right? That was like the world champion and that defeated the world chess champion.
Yep.
And Deep Blue is based on rules, okay? It's based on symbolic intelligence.
Sure.
So, and it's a very, very sophisticated system
Yeah.
of rules, you know,
Mhm.
or what we call experts. Well, AlphaZero defeated it. And AlphaZero actually was based on taking pictures of a game of Go and deciding of what the next picture should be.
Mhm.
This is how we define moves. Okay.
Yep.
I have a picture of the game, and this is what this picture should be the next time I look around. And it defeated this other system that knew the rules of chess, and you know that knew strategies and was trained on what world chess champions did and so on. Still, this other system that was based on pure images defeated this other system that was based on rules.
Mhm.
And here we can see again that these systems actually are very, very efficient at doing things without even knowing what they're doing. In fact, they can't even define the problem that they're trying to solve.
No, you've already presumed the answer to your question. You say they don't know what they're doing. Who's to say they don't know what they're doing any less than Deep Blue does? You've already decided that a certain class of solution is what you're going to call knowledge and understanding. And then your complaint is that this other system that's better at the task doesn't use this solution. But that's you presupposing the nature of understanding and knowledge.
Okay, let me intercede and say that you're both Wittgensteinians here, because you're both second guessing what the meaning, what the usage of the word understanding is.
Yes, I agree with that.
Okay, so in that respect, you're similar. Munir has a different understanding of understanding or what have you. But what I was suggesting with the example that I gave, is that there's a lot more to it, to that, what's behind that word than just usage. It feels like something to understand something. And if that feeling isn't there, you're not understanding it. You may be doing addition. Look, you've had algebra students who can factor quadratic equations by applying the algorithm, but they have no idea what a quadratic equation really is and means. They don't understand, but they're doing something. And nobody denies that with methods, predictive methods like this, you'll probably get most of the things that can be done, especially if you're allowed to take giga data of images, etc. But that's not understanding. That's a shadow, an epiphenomenon of understanding. It's not understanding.
I just don't know what that means. When you say that there is this thing, that what it is like to understand, I just, the words wash through me and I recognize them as grammatical, but it's equivalent to saying colorless green ideas sleep furiously.
Well, that's not a bad example either, because that does mean something. But I'm sorry, I'm going to do it to you again just once. Did you notice that it was different to hear those words from the words that I'm speaking now? Is that difference a difference in feeling or just a difference in the usage of the word understanding?
In my opinion, it's just a difference in the behavioral competencies that I have downstream of it. So that feeling you're talking about is just a particular brain state that relates to my ability to respond to it. So when you gave me the sentence in French, I was able to respond to it in a way that was a cogent response that you recognized as an appropriate response to that sentence. And that feeling of understanding was just my feeling that I had that behavioral competence.
You're feeling that you had that behavior. Fine. You were feeling something there. What were you feeling when I was talking Hungarian to you? And what is the system that is doing the predictive system with one of your predictive tests? What is it feeling? The answer is nothing.
Well, nothing. we don't know that. We can't say. This is where I think, for me, ultimately, I guess, if I'm clear on this, I just think Alan Turing was right. Like, that's honestly where I'm at on such matters, right? I don't think we can ask the kinds of questions that you really want to ask here. We can't really get at those things. We can't, like, the things that you ultimately want to be asking are not things that we can ever address. What we can do, the only thing we can do, the only coherent thing we can do in science is ask the question, what is required to get an agent to exhibit the behaviors and cognitive capabilities that make us inclined to use the word understanding.
But don't you think this is like sweeping the dust under the rug?
I think it's just being honest about the limits of language.
That's turning,
and the realities of human cognition.
You're turning cognition into an engineering problem.
Yes, quite.
Okay. And I dispute that. By the way, I'm an engineer by training, okay? And actually I gave up on that because to me, there is no intelligence there, okay? There is only technology. And in fact, I'm really surprised that Turing said this actually.
He didn't say that. Let me set the record straight and then I'll give it to Jonas. By the way, I also agree with Turing, and Turing was not a Wittgensteinian. All he said was—
No, he wasn't. I'm taking a Wittgensteinian interpretation of why Turing was correct.
What he did say was, it was partly mistaken, but the spirit was right, was that if you want to ask questions like, does a system that passes what was eventually called the Turing test, a computer that could pass a Turing test, is that computer really understanding? If by that you mean something like a subjective state, a state that he said solipsism, but that wasn't what he meant. He didn't mean that. But all he said was that questions of that sort cannot be addressed by my method. He's not saying that there's no such thing. He just said there's—
Oh, okay.
No. Hold on. Let's be clear. It's not that he said that there was no such thing, but what he did say is that there is no way to ask the question that, because he set it up with respect to thought. So he said, here I'm going to address this question of, can a machine think? And he says there's no way to actually ask that question in any kind of real sense. So what instead I'm going to do is I'm going to set up a test which is, in my opinion, getting as close to that question as possible.
Absolutely. I agree completely with you. We're not disagreed about that. That's what Turing said.
Yeah.
And the reason Searle didn't do something stupid and incoherent is because he said, yes, fine, I will now take the system that you claim to be doing this thing, that this is the best we can do with it, there's nothing else we can say, and show that it is not thinking.
Right. So this is where I'm going beyond Turing and incorporating Wittgenstein. I'm saying Searle can't do that. The limits of language are such that Searle's words are effectively meaningless when he tries to engage with that.
Tell me, if someone says this to Searle, if Searle says this in the following way, you believe that this computer, which is passing the Turing test in Chinese, is understanding Chinese, and because computation is implementation independent, if I become the computer, if I execute the very same program that is passing the Turing test, and I tell you with my hand on my heart that I'm not understanding Chinese, are you saying I'm mistaken?
I'm saying that he has set up the conditions such that we have a paradox in the usage of the word understanding, where the people outside of the room use the word understanding and the people who can see inside the room don't use the word understanding. And in doing so, he's rendered it a situation where the word understanding is meaningless. And therefore, his entire point is null and void.
Blake, there's no room. The room is not necessary. There's a computer program.
Because the room determines the usage.
Forget about the room. There's a computer that is executing a program, and somebody's claiming that program is understanding. Forget the room. A program is understanding. It's a computation.
Sure.
Searle does the same computation. He becomes the room in your vocabulary, and he doesn't understand.
No, what I'm saying is the computer program does understand.
Searle says he doesn't, and he's executing that computer program. And
I'm saying that Searle can't say that. The word understanding can't accomplish that. Like the fact is, I'll have to leave at some point soon. Unfortunately, this has been a fun debate. It brings me back to my undergrad years because I did an undergrad in cognitive science and artificial intelligence. Fundamentally, and I suspect very few people here necessarily agree with me, but this is why I'm, ultimately not in cognitive science anymore and instead in AI and neuroscience. someone said this earlier, I do just view it basically as an engineering and natural science problem. The only question that actually exists before us is, what do we have to do to get agents to exhibit the behaviors and cognitive capabilities that make us inclined to use the word understanding? And then in the neuroscience side of things, the question is, what internal neural processes are required for someone to exhibit the behaviors and cognitive capabilities that make us inclined to use the word understanding?
Jonas, Blake has to go. Do you have a real quick one?
Well, I hope it's a real. I hope it's a real one.
Very quick.
Yeah. So I'm just trying to understand. So ultimately, are you implying that behavioral competence is actually a consequence of understanding in the most pure of its form? Is that what your claim is?
Okay, thank you. That's a really nice clarification point. Yeah, my claim would be that you cannot have behavioral competence without understanding.
Right. Okay. Because that's what I'm getting from your, because basically what you're saying is, so understanding would be the learning of an effective path without necessarily being able to identify the reality as we human know it. Am I getting to your claim?
Yeah, like the question as humans know it, I'm not quite 100% sure what that indicates, but roughly yes. Like, because my point is that, you know, we use the word understanding when someone exhibits behavioral competence. We say that person understands in those situations where they exhibit behavioral competence. And so then my claim is that whatever understanding is necessarily based upon usage, the thing that allows us to exhibit behavioral competence.
Okay, thanks. That sounds like, no more comments at this point. That sounds like a very good summary of your position. And I want to express gratitude to you for presenting all of this now. Of course, it will never end. Your undergraduate days are going to keep coming back to haunt you.
By the way, my position is that understanding is an emerging property of the mind.
You'll get a chance to present that one day, Munir.
Yeah.
Okay, thank you very much, Blake. Good luck with your grant. And thanks everybody for attending. Merci à tout le monde.
Oui.
On lève la session maintenant.
Merci à tous. Passez une bonne journée.
Thanks for presenting.